Okay, so today Dr. Hazrat Ali from Umeå University Hospital, Sweden is with us. Dr. Ali is a senior researcher at Biomedical Engineering Research and Development Center at Umeå University Hospital, Sweden. He is also affiliated with a Department of Radiation Sciences at Umeå University, Sweden as a postdoc researcher. His research interests lie in unsupervised learning, generative and discriminative approaches, and medical image processing. He has co-authored over 50 journals, conferences paper, book chapters. Dr. Ali received multiple international grants and awards, including Campi Foundation's grant for postdoc research, Young Researcher Participation Grant from prestigious Heidelberg Laureate Forum in 2017. And he was also nominated in the top 10 Research Pitch Award by the University of Queensland, Australia. So with that introduction, I welcome Dr. Ali. Dr. Ali, over to you. Please, you can start, you can unmute, and also you can share your screen. I'm muting myself, and I also request others, please mute yourself and also turn off your cameras to save the.
Thank you, Dr. Chen. Thank you for the nice introduction, and thank you for having me today. And I'm going to share my screen, and please confirm to me once you are able to see the slides.
Sure.
So I hope that now you can see the slides, and because once I start this slideshow, I won't be able to see the participant list. But
Really, I'm receiving the messages from the audience. They are saying that they have the issue with your sound. Can you please check your mic? I think it's not. It's still choppy. It's breaking.
okay, I can try to speak a bit louder and closer to the
I think
computer.
yeah, we can hear you know more clearly. Yeah. So maybe if you
Okay.
speak loud, then in that way we can hear you better.
Yeah, sure. I can try to speak louder, and I hope that in that way it will be better. So yeah, I hope you can see the slides.
Yes, we can see your slides. You can make it full screen. Thank you.
Sure. So let us start. Thank you again for having me today, and good evening and good morning for those who are in a different time zone. For me, it's almost good night. So my name is Hazrat, and I work at Biomedical Engineering Research and Development Center in Umeå University. And today we are going to talk about the applications of deep learning in musculoskeletal ultrasound images. So a bit of introduction to the research center. We are a small group on ultrasound image research in the biomedical engineering.
I'm sorry,
R&D
just to disturb you again. We still have the issue with the sound. Can you? I'm not sure that how you can.
So
Maybe
is the audio breaking, or is it with the
audio is breaking. Audio is not clear.
Mhm.
So maybe
Yeah, that's strange because
if you are, do you have like the headphones? Maybe if you can just have your headphones, then in that way, like with headphone with the mic, in that way we can hear you.
I can try. Just give me a second. Okay, so I'm talking into the mic now. Is it better? Do you hear me? Okay. Okay, I can see some checks popping up that it seems better. So maybe we continue with this mic and I'll
It's much better. Please continue. Sorry about that.
Okay. Okay, thank you. So I can hold the mic closer to me. So we are a small group in the biomedical engineering R&D, and basically uh, we are affiliated with Mayo University and as well as Mayo University Hospital. So Mayo University got a lot of attention last year. Maybe some people might have seen this picture. The Nobel Prize in Chemistry was won by Emmanuel Charpentier last year in 2020. And she basically worked at Mayo University for almost 9 or 10 years until 2017 before she moved to a different institute. So the university has still her page on their website. Yeah, so it's a kind of an honor. And our group is on the ultrasound imaging research. It is headed by Dr. Krister, whom I work with. So today we are going to talk about our study on the identification of motor units within muscles. So we know that with we study muscles, so typically the clinicians, what they would do, they would use the electromyography, and usually it is the needle EMG where they will put the needle inside the skin, under the skin. So, and in this way, they will try to kind of study the muscles. But we know that this is an invasive method and maybe not so many people would like it. And then we have another approach where we use the surface cathodes. Again, it's not an invasive method, but the challenges with these kind of EMG methods are that they provide only limited field of view. So what can be done here? So ultrasound imaging is basically a good alternative for it, where we can get a much better view of the muscles. So here comes a two-dimensional geometry, a three-dimensional geometry for the kind of problem we are looking at. So if we look at the muscles, we can see that the spatial dimensions of the muscles are not constant. For example, we can see that I see some disturbance. Okay, so we continue. So we are looking at the kind of dimensional slices of the muscles and what happens when there is an activity within the muscles. So basically the motor units will get activated and they will contract and expand, contract and expand. And in this phenomena, they will generate kind of a time signal. So if we look at factor, so we see that there is an increase and decrease in the intensity, which we usually represent by the velocity. So the kind of challenges associated with this are that these motor units, which we call, like the units which we call is the motor units, they overlap in the spatial domain, and their intensity keep on changing. So they can be. So what we propose here is to use a deep learning pipeline for the detection and segmentation of the motor units, and then use a deep learning method to estimate their time domain signal. So the key features associated to the problem is that we do not know in advance that what is the exact number of the motor units which are active at a time. And similarly, the motor units can be overlapping in the spatial domain, and although their spatial location is fixed, the intensity will keep on changing. So we already discussed this, that the way we can study is by using ultrasound imaging, which is not invasive. So there has been some previous work by our group on this problem. What they did was they used basically blind source separation and decomposition of the spatial components, it is a good method, but the problem is that when we have large number of motor units, in the performance of this approach basically degrades very rapidly. So we are now using a deep learning pipeline, and our hypothesis for this is that deep learning can help us to identify the individual motor units by learning the underlying complex interaction patterns. So for that, we use a sequence of ultrasound images to train the model. So here is the general flow. We are having a problem of identification, or let's say detection of the motor units, and then segmentation. So here's the architecture. So the first part of the architecture is basically a 3D convolutional neural network, where we give the ultrasound sequence as the input. The spatial resolution for that is a 64 by 64 input with a 400 with a third dimension equal to 400, which basically represent the time component. And it actually in the spatial domain correspond to 40 millimeter by 40 millimeter of the muscle. And this is a recording of 1 second. So we use this network to transform the data from a 3-dimensional representation to a 2-dimensional representation. Because the next step we are going to do is the segmentation, and for that we need a 2D representation. So next we use a typical mask per CNN, which helps us to perform the segmentation. So for this problem, we have around 10,000 image sequences, and we perform augmentation for the data, which increased the number of sequences to 40,000, and overall they comprise over 700,000 models. When we train the model, it takes around 60 plus hours on a single GPU. And then we evaluate the performance of this architecture using precision and once we are done with the detection and segmentation, the next problem is the estimation of the time signal. So we can have an active motor unit, and then we can also have non-active. So for that purpose, again, we transform the data from a 3D representation to a 2D representation. And once we reach here, we have an output in the form of 8 by 8 by 4. But we need a time series output. So what we do is we use another CNN to transform the data again, and this time we get 256 values to which we can use to train RNN, or recurrent neural network. So the recurrent neural network helps us to predict the time domain signal, and actually get like 1,000 values which we can then combine to get a single. And the way we evaluate this time signal estimation is we use a metric rate of activity. So a little bit about the results. For example, if we talk in terms of the results for the detection, we can see two curves here. So the first one is when we train the model without any noise signal. And then the curve on the right is basically when we train the model by using noisy data. And we can see that when we train the model with noisy data, then it definitely performs a lot better on this data. But a common pattern is that when we increase the number of motor units, then the performance degrades. But of course, the performance degradation on the right-hand side is much less than the performance degradation on the left-hand side, which is basically a phenomenon related to the generalization of the CNN when we train the CNN with noisy data. Again, if we look at the precision curves, we see a similar behavior. We get much better performance when we train the model with noisy data. We do see some degradation in the performance, but compared to the model which is trained with the noisy data, the performance is much
I'm sorry, I think we lost connection.
Professor,
Yes.
uh, I was not able to hear him clearly last 5, 6 minutes. Was everyone able to hear him? Because I lost in between. So, like, I need to check my internet, or was it with everyone?
It's the voice is choppy. Yeah, I can. It's not clear. I requested him to check the mic.
Okay, okay, Professor. Thank you so much.
Hello, Professor.
Yes.
Is there a problem with his connection?
Yes. Yes. So I contacted him. He's trying to rejoin, and I also requested him to check the mic.
Okay, thank you.
Yeah. Dr. Ali, are you there? Are you
Yeah,
back?
can you hear me?
Yes.
Yeah,
So we have the issue with your with your voice. So it's choppy. So please, people are complaining that they are not understanding from last 3 to 5 minutes. I mean, can we try without your headphone, and then we can try with the headphones, and let's see like which would work better.
okay, I can remove the headphones. I don't think the headphones are helping.
Yeah, if there is an
Yes.
issue with the bandwidth, maybe you can turn off your camera and just share your slides and divide. Maybe we can check in that way. If the bandwidth is issue, then it should go in that way.
Yeah, sure. So let me try to turn off the camera and then.
But seems it's mainly the issue with the mic.
Hmm. So anyhow, let us try and let me know if at least you can hear something.
Yeah, it's not clear now. Can you try without your mic, and then we can try with the mic, like your headphone mic, and, or
Yeah,
without.
I have moved the mic actually. I'm directly talking to the computer.
Okay. Yeah, go ahead, please.
So yeah, so I just went to a few slides back because I guess that we missed a few slides. So in terms of the time domain signal, and we evaluate the time signal estimation in terms of the rate of agreement. And if we look at the results, we see the results for detection. So basically, we have trained the model with noise and without noise, and we see that we get much better performance when we have trained the model with noisy data. And it actually makes sense because usually CNNs are trained with better regularization, better generalization if you use noisy data. And then for this precision, we see a similar trend. And similarly for the segmentation, so the performance of the segmentation is naturally dependent on the performance of the detection. So we don't see much difference here, but we follow a similar pattern. So this is interesting here with for the rate of agreement. Again, we see that when we train the model with noisy data, we see much better rate of agreement, almost closer to 90%, even for 10 dB SNR, signal to noise ratio. So here is a sample. On the left hand side, we see 5 motor units which have been detected. And on the right hand side, we see their time domain signal, the activation signal. And we see their prediction or estimation, which very much follow the actual time domain signal. And then we look at 15 motor units. But now the problem is, if you look at 15 motor units, now the problem is that we have overlapping motor units. So we see that, for example, in this particular case, we see that this motor unit number 6, which is somehow overlapped with motor unit number 2. So the model is not able to detect motor unit 6, and similarly, motor unit 8 is also missed. So you do not see any estimation for these 2 motor units. So yeah, we see that when we increase the number of motor units, then there is a degradation in the performance of the model. So this is just an example of how the data looks like. For example, for one contraction, where we have 5 motor units, and then we have 15 motor units. So of course, this study is interesting, but it has some limitations. For example, at this stage, it is only a proof of concept. And if we talk in terms of the deep learning, then of course, learning is involved, which is dependent on a lot of data. And if there is a lot of variation in the data, and which is very much common in case of medical image data, so the learning will be affected compared to the blind source separation method, which does not require any kind of learning. And finally, when we add the noise, then it is a non-physiological noise. So we cannot generalize it, but of course it is good for study and simulation, but we cannot generalize it because the real data will have very much different noise. So there is some acknowledgement here. This is work done in collaboration with Krister, Robin, and Venice. So I would also like to say thanks to the funding agencies here, particularly the Kempe Foundation, which has been funding my postdoc, and also the Swedish Research Council, which provided funding for many other projects of the group. So if there are any questions, I would be very much happy to answer those.
Thank you so much, Dr. Ali. For the students, I will request you if you could send us the slides, then we can share with our students. Very, very interesting talk. Thank you so much. We had some issue with with your voice, but I think that was I think that we somehow weren't able to control. So any question from the audience side? Please type your question if you have, then Dr. Ali would try to answer.
Hi, Said. This is Christopheros.
Yes.
How are you doing? I again, as everybody, I had kind of trouble hearing a lot of the presentations, but just going over with the slides. My understanding is that you're dealing with spatiotemporal data, where space will be a kind of a cross-section that you get from the ultrasound, then you take it over time. But then you apply a 3D convolutional neural network as the first feature. So it seems that you're treating it as a static 3D image in a sense. Where does the temporal aspects come in when you are introducing the RNN? That was not clear.
Yeah, it's a very good question. Maybe because of when we had this problem with the internet, maybe I did not explain it well. So when we basically, before we train the RNN, we are again doing a transformation of the data from a 3D to 2D. But here, if we look at the architecture on the left part in the top left, when we try to reduce the spatial dimension, we are not disturbing the temporal dimension. So we see like 400 coming up in all the blocks. So we do not, so here our goal is not to lose the temporal information. And basically this 400 is like 400 sequences in 1 second. So we do not lose the temporal information here unless and until we are finally flipping the data before we train the GRU. So I hope that actually addressed your question.
Okay, so essentially you are filtering down the image in 2D. You end up with a vector that is, I guess, 8 by 8 by 400, and 400 is still the time. So you're saying you're not losing temporal dimensions, even though it seems that you are filtering in some way across time through the convolutional network because you're weighting all the components at each layer.
We definitely are filtering it, but so underlying that 3D CNN is helping us to kind of extract features which are able to retain the temporal information. What kind of temporal information is that? Of course, we do not we do not dig that, or we are not able to visualize that. But our assumption is that when we try to train the 3D CNN in this way, we at least have the temporal aspect of the data.
I see. I would kind of love to see your paper on this. Maybe it's going to be more clear, but I got the big picture. Thank you.
Yeah, sure.
All right.
I can post.
Yeah.
The link is in the slide, but I can also post it in the chat.
Sure. Thank you, Dr. Ali. So we have another question from audience. So when we are dealing with ultrasound data or X-ray or CT scan, it is actually huge. So to handle processing of such huge data, so how it's not clear. So such as training and validation. So
I'm not sure what is meant by huge. Of course, image data will be huge, and the more data we have, the better it is. But for example, if you look at the first model, so we are using an input of size 64 by 64. So it will be essentially an image data. So even if it is like time domain sequences, but the way we train the model is that we basically save all the sequences in the form of images.
right. Any further question from audience?
And then you perform the training on the GPU, then of course uses the base size, so that will be very much dependent on the size of the GPU. So you can, I guess we use the base size of 8, but that is very much dependent on the GPU.
All right.
I have a question, Professor.
Sure,
So,
you can ask.
Pooja here. So in one of the slide, it was written that identification of individual MUs can be improved by the deep learning. So can you like give some examples about this? Like what exactly do you mean by that line? I did not understand that line.
Okay, I think it can be better explained with this image. If you look at this slide on the left, so basically the black boundaries are actually the motor units. And the color is basically showing their activation.
Their activation, yes.
Yeah, so more bright here means like more tissue velocity or more activation. So this is what we are trying to do with the deep learning model. So we want to identify these regions where they lie actually within the entire spatial domain of the ultrasound image. And then are we able to segment them or not? Yeah.
Is this system more used in the imaging section in the like real world concept right now?
So as we said that this is a proof of concept. So we are not at the moment claiming that it is something we can use in the clinic. But like in the beginning of the talk, I mentioned that typically in the clinic, they will use this EMG, electromyography.
I would definitely like to learn more about this.
Yeah, I think that is like more common. But the issues with EMG is that it provides only, for example, if you look at this figure, So if you look at this, so if we use this needle for recording the data, so we need to insert a lot of needles under the skin, and nobody would like that.
Oh, okay. So yeah.
The challenge is that okay, even if you convince someone that you definitely need to do it, so the challenge is that this needle will provide a very localized signal, right? Recording at only one specific location. The same is true for even like surface cathodes. So we use surface cathodes, so we are avoiding the use of needles here, and that's great. But again, the signal will be very much localized.
Okay, something
Compared to
similar.
this,
Sorry, go ahead.
yeah, but compared to these, if we use an ultrasound, so we know that ultrasound provides imagery for entire spatial resolution.
Oh, okay. Thank you, Professor. Dr. Ali.
All right, thank you so much. Okay, so we have another question from Michael. Is there ever an instance where noisy data would be considered a substantial amount of the data points, where filtering it would leave out a significant portion of data?
Can you please repeat that? I'm not sure.
Sure. Is there ever an instance where noisy data would be considered a substantial amount of the data points, where filtering it would leave out a significant portion of data? Michael, you can unmute yourself and can please clarify your point. It's not
Okay, so the way I interpret this question is basically he's asking that is it possible that the noise is actually behaving as a data? Is that true? Like this is what you are asking, and that's actually a very good question. I cannot say yes or no, but definitely the noise has impact on the training of the CNN, and it's not just specific to this CNN. If you look at the theory of CNNs and the theory of neural networks, I think it's very common. Whenever we use noisy data for training, then the model is expected to, and it should at least be having like better regularization, which means that better performance on the test set. Secondly, we know that in the test data, there will always be some noise. So if we do not use noisy data for training, then we can expect much degradation in the performance. Thirdly, we tested only for 10 dB SNR and 20 dB SNR. So I think there's like more common values we use for testing with noise.
right. Another question.
Yeah, the ultrasound data is simulated ultrasound data. And because we compare with the blind source separation, which is again study from our work, so we use the same data which has been used by the previous work, but it is simulation ultrasound data.
Last question, and we have a room for one more question. If anyone has, please ask. You can unmute or you can just type. All right. If you guys don't have, thank you. If you don't have any question, I have a question. When you consider, for example, applying the deep learning, machine learning algorithm real time, especially as you have the use case for like for the human, then there is an issue with the adaptability, and the peoples are trying to help deal with this problem with the explainability in the AI. So in future, how you are planning to deal with this? Like if everything would work after a few years, you would like to apply your research in real time, then how that would help or satisfy to the people or to the hospital management to really deploy real time your system?
Okay, so that's actually a very good question and a very good comment. So basically, it is always the case, like the ultimate goal is to bring these models into possible use, clinical use. I think in this particular case, our group is quite lucky because we are located inside the hospital, and a lot of like ultrasound operators as well as technicians and as well as like medical doctors are available to us. And actually some of them are like close collaborator of our group, and they already have joint publications as well. So I think this a bit of a positive thing for us that we can get immediate feedback whenever we need it from you. But yes, when will these be ready for clinical use? There's, I think, a different thing. And like you mentioned, the explainability of the model, when that is something we have not addressed, at least in this work, but definitely we would like to consider it for like future work where we can get much better explainability of the, let's say, CNN or cycle GAN or any other model.
All right. Well, thank you so much. With that, we thanks our speaker from the our college and our university behalf, and thanks, Dr. Ali, for your time. And few people are asking about your slide. I will contact with Dr. Ali and will get the slides, and I will also look at the video if I'm not sure what would be the quality. If the quality would be sufficient to share, I will definitely share the recorded video as well. With that, thanks all for joining, and please don't forget to sign up for our next webinar, which would be on October 28th. And our speaker will be Dr. Saeed Samit from University of Windsor, and he will talk about the privacy preserving protocols in healthcare informatics. Thank you.
So thank you, Dr. Chen, for having me for this talk, and thank you all the participants, despite the poor quality of the audio perhaps, but I don't think there was much we could do. We actually tested this before the talk and it worked quite well for us, but